What's up, everybody? Welcome to Lecture 29. Lecture 29 is all over sections 6.6 to 6.8. Now, some of you may be looking at your notes and that arrangement of section numbers saying, whoa. What about 6.1 through 6.5? Great question. The reason why I am glossing over those is because we've already covered all that material either earlier in the semester in a direct way or through just other sections and examples throughout the semester. So for that reason, I thought it was okay to just kind of gloss over those. That said, I do encourage y'all to read those lecture notes if you're looking at some of that stuff saying, oh, wait, I don't remember us talking about it. Okay, fine, that's fair. Look at your lecture notes though, because they do talk about all of this, right? I repeat a lot of stuff in those sections that we've talked about in other sections. So like I said, I'm just glossing over it for that reason. And you may also be looking at this saying, I remember in lecture 13 us talking a little bit about section 6.6. Yes, you are correct. We did talk about section 6.6. But I wanted to touch on it again. One, because outside of that lecture 13, we really haven't talked a whole lot about it. And two, because there's an integration problem that I think is a good example problem of U-sub that I wanted to go over that uses inverse trig functions, and because there is a relationship between trig functions and hyperbolic trig functions that I wanted us to talk about as well. So I thought it was a good lead into other lecture material. So having said that, really quickly, we've got this table here of the derivatives of inverse trig functions. For those who do not remember how we arrived at some of these, I would recommend you go back to lecture 13. I think it's about a third of the way through that lecture where I get into some of these inverse trig examples. But really quickly, I just wanted to write out this table to help refresh our memory on what the different inverse trig derivatives were. And the reason why is because the example we're about to see is going to use one of them. But it's going to use one and some tricks that we can apply to integration that I thought made it worthwhile to actually just see these again. So, without further ado, your lovely inverse trig derivatives. Having said that, let's check out this example I want to talk about. All right, so the example that I wanted to look at is this integral right here. The integral of 1 over the quantity x squared plus a squared integrated with respect to x. You may be looking at this and the derivatives of the inverse trig functions that I left up and can kind of guess at what the solution to this will be. If that's the case, I will quote one of the great companions of Doctor Who and just say, spoilers. But the way we're going to go about this is we're going to start by multiplying by 1. Now, what do I mean by that? Well, I mean, we're going to represent 1 in a very particular way. And when we do, and we multiply that 1 by this, or rather this by that 1, we're not going to change anything. We're just going to get a new way of writing this. And by doing that, we're going to be able to work out what our solution is. So what is it we're going to do? Well, we're going to observe that 1 is equal to 1 over a squared divided by 1 over a squared. Okay, yeah, that's obvious. But when we multiply this by this, that's when we're going to get some rearrangements. So let's do that really quick. Integrating 1 over a squared over 1 over a squared times 1 over the quantity x squared plus a squared integrated with respect to x gives us, well, check it out. We could distribute this 1 over a squared in the denominator across this denominator, right? Like once we distribute all of this, we're going to get some things that we can work out. See what that looks like. This is going to give us 1 over a squared over the quantity x over a, that quantity squared, plus 1, integrated with respect to x. Now what? Well, now we're going to make a substitution. We're going to look at this and we're going to say, you know what? I think if I were to set u equal to x over a, then necessarily du dx is going to be equal to 1 over a, meaning that dx is equal to, or rather du, my mistake, du is equal to 1 over a dx. So now we can rewrite that integral using a bunch of u's, right? Because see, we do have a 1 over a dx. We're just going to use this to form that. And we do have our u. So using this substitution, we're going to get the integral of 1 over a divided by u squared plus 1 du. Well, hey, the integral of 1 over u squared plus 1 is just arctan of u. So this tells us then that our integral is equal to 1 over a times the arctan of u plus a constant. But hey, wait. Don't we get that u is equal, or didn't we say u is equal to x over a? So substituting that back in then, we get 1 over a times the arctan of x over a, all of that plus a constant. And that's it. That's all there is to it. So let's keep moving on. Next we're going to talk about the relationship between hyperbolic functions and trig functions. And that's just really to prep us for what hyperbolic functions even are. And I'm going to be honest, it's going to get weird for a second. So hold on and just go with it for a minute. All right, so to talk a little bit about the relationship between hyperbolic trig functions and trig functions, we need to know some background information about the geometry that they're describing. Now we all know that x squared plus y squared equal to 1 describes the unit circle, right? And we can parameterize the unit circle as cosine of t, sine of t. So if we had this variable t, we could pass t through cosine and say x is equal to that thing. And then we could do the same thing for y except with sine, and that would describe all the points on the unit circle, right? That's trig 101. Now, on the other hand, there's this other geometry called the unit hyperbola. Unit hyperbola. And what it is x squared minus y squared equal to 1. And it's this thing. Now, the points on the unit hyperbola can be parameterized using hyperbolic cosine of t and hyperbolic sine of t. Sometimes you'll hear this called cosh of t and this called sinh of t. I prefer just to call it hyperbolic cosine and hyperbolic sine. But this doesn't really explain why these two things relate to each other, not yet. To understand that in a geometric way, you need to understand this idea of conic sections. Now, conic sections are the geometries that you get by intersecting a plane with these two cones. In other words, take two cones, one facing down, so the point expands upwards, and then the other one so that the point expands downwards. If you were to take a plane, just a sheet plane, so think a flat piece of paper, and intersect that horizontally with these cones, well, the intersection between the cone and that plane will take the form of a circle. Now, it's important to note, we're not talking about the cone as a solid object. We're talking about just the surface of it. So the surface of that cone intersecting that plane forms a perfect circle, if that plane is horizontal. Okay. Well, what happens when we take that plane and rotate it so that it's directly up and down? When we do that, the intersection between the cone and the plane will then form these hyperbolas. You can also get ellipses by moving that plane in different directions. You can also get parabolas. So conic sections describe the way, the shapes that you get, the graphs or shapes, however you want to think of it, that you get by intersecting a plane with these cones. And you can get, like I said, a circle, an ellipse, a parabola, or a hyperbola. Okay, so that's the geometric relationship. What about what's called analytic relationship? How are these things mathematically, algebraically related? Well, hyperbolic cosine of the imaginary number times x is equal to cosine of x. And the hyperbolic sine of the imaginary number times x is equal to negative I times sine of x. Okay, so this gives us a kind of idea of what hyperbolic cosine and hyperbolic sine are. But it doesn't really give us a nice understanding of it, right? So what exactly are these hyperbolic sine and cosine? What do they look like mathematically, algebraically, beyond just this cosine and sine thing? For that, stay tuned. That's what I'm about to show you all in just a second here. All right, so we've talked about hyperbolic cosine and hyperbolic sine a little bit. I'm going to introduce this new idea of the hyperbolic tangent. The hyperbolic tangent is just the hyperbolic sine divided by the hyperbolic cosine. But again, what's the hyperbolic cosine and what's the hyperbolic sine? Well, the hyperbolic cosine is e to the x plus e to the negative x, that quantity divided by 2. And hyperbolic sine is equal to e to the x minus e to the negative x, that quantity divided by 2. Now check something out. Look what happens when we apply the derivative to the hyperbolic cosine. Well, this is d dx of the quantity e to the x plus e to the negative x, all divided by 2. Using the rules of the derivatives, we can break this up a little bit to get 1/2 d dx of e to the x plus d dx of e to the negative x, which gives us 1/2 times the quantity e to the x minus e to the negative x, which is equal to e to the x minus e to the negative x, that quantity divided by 2. But hey, that's hyperbolic sine of x, isn't it? And something similar happens when you take the derivative of hyperbolic sine. In other words, even their derivatives act like tangent or trig functions, which is really cool when you consider everything that we just talked about. We just talked about the geometry of it, and we just talked about the algebra, and somehow all of those things come together to mean even their derivatives behave the same way. That's cool. That's awesome, actually. Now, a question might arise. How the hell are these things equal to our, or how are they related to our sine and cosine functions in the way that they are? Like, how do we go from this to the way they relate to sine and cosine? That's weird, right? That seems like a leap. After all, if that's the case, why don't we have sine and cosine written in terms of e to the x? Well, we do, but we have to use a trick. And I'm not going to show you the entire method here. I'm just going to show you what that trick is. And I want you to think about it, because it gets at the heart of the geometry and the algebra and the analysis that's happening here. Because there's a lot of cool, good, genuinely good math that's going on underneath the surface here that gets into all sorts of crazy things, some of which are related to like prime numbers, general relativity, and all other fields, all sorts of different fields. But that particular relationship that allows us to say cosine of a, or the hyperbolic cosine of I of x is equal to cosine of x, what we're using is taking advantage of Euler's identity. Euler's identity tells us that e raised to the imaginary number times t is equal to cosine of t plus the imaginary number times sine of t. Now, another just cool application of all of this, I said it applies to general relativity, because it does, special and general. But one implication of this actually showed up in the 90s during Desert Storm. During Desert Storm, it was one of the first times we had rolled out this weapon system called MLRS. Some of y'all who are in the Army are probably familiar with it. It's a multiple rocket launching system. And it's basically this big camouflage box on tracks that has a back that lifts up and launches a bunch of missiles. Rockets, I should say. Okay, well, how does that relate to this stuff? Well, when we rolled it out, there was a problem with it. The satellites that were helping us guide the rockets to their destination. So the difference between missiles and rockets are missiles can actually change trajectory. Once they're in the air, a rocket can't. So these things had to know where they were going the moment they were launched. In the satellite system that we were using, in the programming that we were using, all the work that was going in the back end didn't remember to apply relativity. And relativity tells us there's this thing called time dilation. So the faster you go, the slower time appears to move for you compared to the things that are stationary around you. Well, because of this oops, the rockets were missing their targets by like relatively large margins. And some of that math is this stuff here. So this actually has application in the real world that cost us money, big money, and potentially lives. So why do we care about this? We care about it because it's real. It actually touches our lives. And because it's at the heart, the intersection of a bunch of good, cool, genuinely awesome areas of mathematics, geometry, complex analysis, arguably real analysis. You get into differential equations. You get into all sorts of just crazy cool things. You can talk about weird spaces like hyperbolic spaces and what that means and how that relates to functions and how that relates to the calculus in those spaces, because we don't actually know how calculus works in every space. For example, a donut. It's really hard to do calculus on the geometry of a donut. We call that a torus. So there's all these different cool areas of math that relate to this. And that's why I wanted to take the time to actually work us through some of that relationship between trig and hyperbolic trig functions, as well as some of the calculus behind it and the geometry and analysis of it. Because it is just genuinely cool. And it does have huge implications for our day-to-day lives. If we didn't know this stuff, the modern era would not be possible at all. At all. And you have Hilbert and Einstein to thank in part for that, as well as arguably Joseph Fourier, Riemann, Euler, and a couple others. But yeah, this stuff's dope. Having said that, we're going to move on now to another concept. It is, I think, section 6.8. The idea is what's called L'Hôpital's rule, or L'Hospital. Most people call it L'Hôpital because apparently the S is silent. I don't know. But we're going to move on to that. So to start off our conversation about L'Hôpital's rule, let's start off with a question. What's that limit given either of those conditions are met? Well, that's going to give us 0 over 0 or infinity over infinity. Well, that is what's called an indeterminate form. An indeterminate form is just a form that is exactly what it sounds like. It's indeterminate. You can't tell anything from it. What is 0 divided by 0? You can't divide by 0, so what is that? What's infinity divided by infinity? Well, I don't know. There's a bunch of different infinities. Which one of them is it? Is it the countable infinity, the uncountable infinity? Is it is it one of the several different forms of infinities? We also have infinity minus infinity. We have 0 times infinity. 0 raised to the 0th power, because after all, what does that mean? Anything raised to the 0th power is 1, but a power is a multiple of a value with itself or some sort of fractional power, right? So what's 0 times, is that 1? Like, I don't know. What's 1 raised to the infinite power? Does that even make sense? We multiply 1 by itself an infinite number of times. Shouldn't that just be 1? And what's infinity raised to the 0th power? These are all indeterminate forms. And these forms or what L'Hopital's rule is meant to solve. That's what we use it for. It's when these things show up in a limit and we say, oh, if I know. That's when L'Hopital comes around and we say, all right, cool, now I can actually solve this thing. Now, what L'Hopital's rule says exactly is, given that these conditions are met, this limit is equal to the limit as x approaches a of f prime of x divided by g prime of x. That's it. This is L'Hopital's. That's all it is. L'Hopital says if you get one of these two forms, then this is actually equal to this. Cool. Okay. How the hell does it help us solve this stuff, though? And these first two, that's obvious, but what about these other examples? That's what we're going to be talking about now. But really, ultimately, all we're going to do is we're going to turn each of these problems into one of these forms. So let's see how we might do that. All right, so for our first example, we have the case of the limit as x goes to 0 of the quantity cosine of x divided by x minus 1 over x. Well, if we were to apply the limit directly onto that, we'd have this case right here, right? Infinity minus infinity. That's no bueno, though. It's an indeterminate form. So we need to use L'Hopital's somehow to make this into a solvable problem. To do that, the first thing we should notice is that we have a shared denominator. So we can bring all of this into one fraction, giving us the limit as x goes to 0 of cosine of x minus 1 divided by x. All right, so how are we going to apply L'Hopital's? Well, first we need to identify what our f of x and our g of x is. I think that seems pretty obvious in this case. Let me find blue chalk, that's what I wanted. For f of x, let's set that equal to cosine of x minus 1, and for g of x, let's assign that to be equal to x. Well, in that case, our derivative of f of x, so f prime of x, is equal to just sine of x, right? My mistake, negative sine of x. And the derivative of g of x, so g prime of x, that's just going to be equal to 1. So by L'Hopital's, we know that this thing is equal to the limit as x approaches 0 of our denominator, the derivative of our, my mistake, the derivative of our numerator, negative sine of x, divided by the derivative of our denominator, 1. Well, this is equal to the limit as x goes to 0 of negative sine of x. And that's just equal to 0. And that's it. That's all this is. That is all we're doing here. There is nothing else to this. You are just taking the functions and rewriting it in some way to be related to L'Hopital. So you're trying to put it into that fraction form. You're taking one of those, blah, 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 blah. Words are not happening. You're taking one of those indeterminate forms and turning it into something you can apply L'Hopitals to. That's it. Well, that's all well and good, but what about those power examples? How does that work? Because I don't see a clear way of applying L'Hopital to that. I'm happy you asked. Let's check that out. Now, in the case of the products, so 0 times infinity, for example, the way we're going to go about that is by recognizing that we can rewrite the expression f of x times g of x as f of x divided by 1 over g of x, or as g of x divided by 1 over f of x. So we can rewrite this in a couple of different ways. But notice what that does is it gives us a way of putting this in terms of L'Hopitals. Now we have a function divided by a function, or a function divided by a function, which is L'Hopitals, right? And that's the idea. We're just going to use these sorts of tricks all the way through. Just like you just saw with that sum and difference example, we wanted to rewrite that in terms of a function divided by another function. We're going to do the same thing with the product form. But that brings us to a new question. What about the powers, the exponential forms? Happy you asked. We'll see that in just a second. Now, to solve that exponential case, we need to take a moment to recall two different facts. First, we could rewrite the function f of x as e raised to the ln of f of x. We also know that the limit as x approaches a of e raised to some function is equal to e raised to the limit as x approaches a of that function. And we need those two bits of information to help us solve this question of how to apply L'Hopitals to those exponential cases. We need that because what we're going to do is we're going to apply the limit as x approaches a to f of x raised to the g of x. But this thing, because of this, in yellow up here, is equal to the limit as x approaches a of e raised to the ln of f of x, that natural logarithm, times g of x. And because of this, we can apply the limit to that exponent. So now we have e raised to the quantity, the limit as x approaches a, of the ln of f of x, that natural logarithm, times g of x. But notice, what that means then is we only need to worry about this little bit here. Let me erase this over here. Because we're able to bring this limit up into the exponent, now we've just reduced that limit to solving this problem. This is the limit as x approaches a of the ln of f of x, that natural logarithm, times g of x. Once you do that, once you solve that limit, just plug it into the exponent. The end. So whatever this is, let's say it comes out to be, I don't know, c. Well then, your answer is e to the c. That's it. That's how you would do it. But the catch is noticing that this is exactly like that last example. What you're doing is you're turning the exponent into the product of two functions. And since you can apply the limit directly onto that exponent, well then this is just like solving the limit of the product of two functions. That's it. That's what this idea is, and that's all L'Hopital requires. Just some MacGyvering of the math. Of course, you gotta keep within the rules, but it's just MacGyvering of the math. That's it. Having said that, there is a problem in the notes that I'm gonna leave for y'all to play with, because I want you to get practice with this. I do want you to look at the notes. And that problem is to show that the limit as x approaches 0 of the cosine of x raised to 1 over x is equal to 0. Now notice, this is an indeterminate form, right? This is like 1 raised to infinity, if you were to apply that limit directly. So you have to use this exponential trick that I was just talking about to this problem. And as a hint, you should eventually end up with the limit as x approaches 0 of negative tangent of x is equal to 0. And that'll tell you how to do the rest of this problem. Okay, stop. Wait, pause. Wait a minute. I just realized I made a mistake. There is a typo on the board. This is not 0, this is 1. Now, you're free to go. If y'all have any questions, by all means, feel free to shoot me an email, come by office hours. But yeah, that was a typo. That was not supposed to be the limit as x goes to 0 of cosine of x, all of that raised to 1 over x is equal to 0. It was not supposed to be equal to 0. This is supposed to be equal to 1. So, sorry about that. Which should have you scratching your head looking at all of this. It's a good problem. Like I said, I want you all to play with it. Having said that, y'all free to go. Have a good rest of your day, everybody.